Hi everyone, so today we're just going to be talking about section 10.1, which is an introduction to parametrics. And if you're here because you want to know how to find slopes or second derivatives of parametrics, you're actually probably going to want to go to section 10.2, which is parametrics with calculus. And this is just going to be a quick intro on what parametrics are. So in our math career so far, we've probably dealt with a lot of functions in the form of y equals something. For example, y equals x squared, or y equals the sine of x, or something like that. But what if you have a function like this? Well, it's not actually a function because it doesn't pass the vertical line test. But what you can do with something like that is you can still describe it by using a set of parametric equations. So when you're given a set of parametric equations, you'll usually have x equals something and y equals something. For example, x could equal 3 sine of 2t, and y could equal -4 cosine of 2t. And in this case, you'll see that there are actually 3 variables, x, y, and they're both defined in terms of t, which usually stands for time. And t is called a parameter, the third variable by which the other two are defined. And when you have a set of parametrics, you can also graph it like an xy graph, but you wouldn't actually graph the variable t. T is useful though because not only do you know where a point is because of x and y, but you also know when it gets there, which is a t. So, for example, what do you think this graph would look like? Well, there are a couple ways to look at this. So the first way is to try and get rid of the parameter t and actually just find an xy equation. And it would be really difficult to use a simple substitution here because sine and sine inverse, it would be really ugly and hard to graph, but we can use our trig properties to solve this actually. So we already know that sine squared of anything plus the cosine squared of anything equals 1. So if we square both of these equations, first let's manipulate it a little bit to get x over 3 equals the sine of 2t, and y over -4 equals cosine of 2t. And squaring both sides, we'd get x squared over 9 equals sine squared of 2t. Y squared over 16 equals cosine squared of 2t. And adding these together should equal 1 because it's sine squared plus cosine squared is something. So that would give us x squared over 9 plus y squared over 16 equals 1. And this should look like a pretty familiar form to us all the way from Algebra 2 because it's actually an ellipse. And we can see that because the number under y is bigger, it's actually going to be taller than it's wide. So we can already sketch this graph just by getting rid of the parameter t. But sometimes you won't always be able to find the parameter t, get rid of the parameter t. And in that case, you can just make a table with t, x, and y. Another thing is sometimes when they give you a set of parametric equations, they'll also give you a range of t to look at. For example, they'll say 0 is less than or equal to t is less than or equal to pi. And this isn't always the case, but if it is, then you just have to graph the areas where t is in this range. So here, let's try to graph the set of equations with this limit. You would start with t equals 0, and then it's just a simple substitution into x and y. You're just dealing with 2 variables at a time, and it's just a t-chart like you used in, Algebra 1. So 3 sine of 0 is 0, and for y, we have cosine of 0 is 1 times -4 is -4. So we can just start sketching that graph here, 0, -4. And then let's just pick some nice numbers to work with. Pi over 4, that would give us 3 for x and 0 for y. And once you start drawing this graph out, you can start connecting it and you'll see that it does match our ellipse and exactly what we would expect from the x and y equation. They're the same equation, just in different forms. X and y were parametric. And another thing is you can see that at the beginning of the range we're down here and we're tracing out the ellipse this way, counterclockwise. So one thing you need to add to your graphs of parametrics is some sort of arrow indicating the direction of movement of the graph. So over here, you could draw an arrow like this. And let's just continue filling out this table. And I won't show all the work, but you can probably guess what the points would be. Pi. And at the end, we get back to 0, -4. And just draw some arrows indicating that this ellipse actually transfers counterclockwise. And we see that in the range from 0 to pi, we trace this ellipse exactly once. But sometimes you'll have a range where maybe if it was from 0 to pi over 2, you would actually only trace it out 1/2 of it. Or if it's 0 to 2 pi, it'd still be the same graph, just 2 times. And of course, sometimes you won't have this range, and you'll just have to graph it by putting nice values and trying to get all of it. So another way of using parametrics and graphing something is obviously with a calculator. So I have a TI and Inspire, but you would just go to Graph and Menu, Graph Entry Edit, and 3 Parametric, and just input what they give you, which is x equals 3 times the sine of 2t, and y equals -4 times the cosine of 2t. And here you can even put in the range, which is here 0 to pi over 2 pi. So I can just put 3.14 or something. And yeah, it's just what we expect, except the step size may not have been right, or I didn't put in enough decimal places, but it is an ellipse. And that's about it for parametrics. And they're pretty useful because later you'll learn about polar equations where we'll have r equals something, and you'll have to split it up into an x and y parametric. And that's all for today, and good luck on the final. Bye!